Next up, we have Felix. Felix is a research scientist in the Foundational Cryptography Group at IBM Research Europe, Zurich. And before that, he was a postdoc in the Applied Crypto Group at ETH Zurich. And Felix actually has a lot of experience with applied cryptography. In his research, he has contributed to the analysis and improved security of protocols like TLS, QUIC, and Signal, as well as their underlying building blocks. Today, he's here to tell us about the properties of key encapsulation mechanisms, which are very important in practice, but not always achieved by standardized and deployed keys, namely obfuscated public keys, and verifiable decapsulation. So to give just one example of why these properties are important, obfuscated public keys are a requirement for cake, which is one of the few actually KEM-based PAKE protocols, thus making it a possible avenue towards a hybrid PAKE, which achieves both post-quantum and classic security. But Felix will tell us more examples of why these properties are important, so the floor is yours.
Thank you very much. Thanks for having me at CAW. It's a pleasure to be here, and thanks for all the effort that you put into organizing, setting it up, and the tech equipment over here. I really appreciate the effort that you put into running this also for remote participants. Right, so as I said, this talk I'm going to tell you about some new and advanced concepts for KEMs. So KEMs, or key encapsulation mechanisms, are of course one cornerstone building block for the quantum safe transition in particular. However, the standardized schemes, the standardized post-quantum schemes that we have today don't always fit the bill for all the deployments where we want to use them, where we're using Diffie-Hellman today, for example. And sometimes implementing them can be brittle. So in this talk I want to present two new ideas, which kind of tackle some of these issues, which is obfuscation and hybrid obfuscation on the one hand, and verifiable decapsulation, or what we call verifiable decapsulation on the other hand. This is based on joint work with Louis Blabusch, Kathleen Hüffelmans, Mike Rosenberg, Douglas Sibila, and Shannon Beach. And the talk is kind of split into these two topics. I'll start with the first one, with obfuscation. Let's see. There we go. So modern internet security protocols more and more don't only aim to hide the data that you're sending, the actual content you're sending, but also metadata. This is primarily, of course, to protect user privacy, but also for other reasons. For example, if you want to avoid censorship, you might want to hide the fingerprint of your protocol. You want to kind of dissuade people being able to tell what protocol you're actually running. And there's also the issue of network ossification that has been popping up here and there, primarily with the deployment of TLS 1.3, where basically middle boxes assume that a protocol will always look the same way. And in order to prevent that, you try to kind of hide what protocol you're running so that people can't kind of tailor middle boxes down to a specific design. So this kind of metadata hiding happens in TLS 1.3, for example, with encrypting the initial client hello, hiding the server you want to talk to. QUIC is doing some encryption of the initial data you're sending to look like random stuff to prevent this type of network of ossification. And then primarily the motivation for us for this work was OPS4 and Shadowsock's tools used for censorship circumvention, which essentially try to look like completely random strings on the wire. And so these protocols are often referred to as fully encrypted, or look like random, but mostly fully encrypted protocols. And one interesting aspect here is that beyond the data encryption, you also have to have the initial key agreement look like completely random strings. So what do these protocols do today? Mostly you're running a Diffie-Hellman type key agreement, so you'd apply the Elligator encoding to turn these Diffie-Hellman group elements, or elliptic curve points, into random looking bit strings or byte strings on the wire. Now, if you're thinking about the quantum safe transition, for example, the ML-KEM public keys and ciphertexts that you would send instead don't look like random strings, so you can't directly deploy ML-KEM in that set. To give you an illustration of that, so if you would plot kind of how the distribution of ML-KEM public keys for ML-KEM 68 looks like on the wire, you get this kind of heat map. You see a well-distributed siding on the right, and then some biases on the left. And these biases come from the coefficients of including the public key, which have their most significant bit bias towards 0. And that's what you kind of see and can immediately tell on the wire, and that's how you would tell apart an ML-KEM public key from a random string. So that's kind of like the issue, and the solution we're proposing is what we call Kemeleon. It's kind of like an Elligator-style encoding of ML-KEM public keys and ciphertext. And I'll walk you, just to give you a glimpse of how this works, through the details of the public key encoding. So in more detail, as mentioned, ML-KEM public keys have these vectors of coefficients, and these coefficients are modulo prime q, 3329, and encoding these coefficients individually is what ML-KEM public keys are doing. So they're represented in 12 bits, which means the leading bit of each of these coefficients will be biased, and this is precisely where the bias away from a random string comes from. So what we do with Kemeleon is we first of all accumulate all these coefficients into one big integer, which means we have one remaining bit which is biased, the leading bit of that big integer. And then we do rejection sampling to reject if this most significant bit is 1, throwing away some part of the key space kind of. For ML-KEM 768, rejection happens with roughly 17%. Actually, better than what you have to do in Elligator, where you also have to you can't encode all the keys. One interesting side effect of the encoding is that the resulting public key actually gets a little smaller. So roughly 2.5%, not a lot. But if you're really trying to squeeze an ML-KEM public key into some constrained space and you're lacking like 20 bytes or 30 bytes, Kemeleon might be interesting not only if you're looking for a random representation, but just a more like a shorter representation. So this is very roughly what Kemeleon does. For ciphertext, there's a bit of an extra caveat because ML-KEM ciphertexts are first compressed. So for the encoding, we have to first actually need to decompress them to get to a uniform space, and then do the encoding similar as for the public keys. But I won't go into the details of it. So if you then combine Kemeleon with this encoding with the basic ML-KEM scheme, you get a drop-in replacement for a classic Diffie-Hellman Elligator exchange, where you replace the public key and the ciphertext exchange with a random key, so with a random string. And we actually formalize this in this work under the notion of an obfuscated KEM. So an obfuscated KEM is one where public keys and ciphertext look like random beyond the regular properties you want. So just to recap those, ML-Kemeleon, this combination, of course, still achieves in CCA security. It has strong what's called SPR CCA security, meaning that the keys look random, and you can simulate the ciphertext. This is an important property if you care about anonymity of the KEM. That has been used before, and the new properties is the last line here, which says that we can show that you, under certain assumptions, LRBE-based assumptions, the ciphertext and the public keys look uniform, look indistinguishable from a random string. And now Kemeleon has been picked up by the IETF, the CFRG working group. It's adopted as a work item there now, so we're on the way to kind of like make a canonical version out of that. This draft actually includes further variants, one where you can avoid the rejection probability, the rejection failure, at the cost of slightly slightly larger public keys again. There's a deterministic variant, so I'd be super interested if you have applications where Kemeleon, that kind of technique comes in handy. We want to kind of like narrow the choices down in this IETF draft. So if you have opinions, please come talk to me. I'd be happy to chat. So this is kind of like the way to turn ML-KEM public keys and ciphertext into random strings, and like to migrate from a Diffie-Hellman protocol to a KEM-based one. Now in practice, often, of course, you don't want to do that migration directly. You usually want to go through some hybrid where you combine Diffie-Hellman and ML-KEM, for example, in order to safeguard against failures on either side. Now, for a hybrid KEM, the classic approach is what I will now call the parallel combiner approach. You take the two KEMs, you encapsulate against both of them, you mix the key material together, and you concatenate ciphertext. This is done literally everywhere. This is in TLS 1.3, in HPKE, in XSpring, and all other combiners that have been discussed for hybrid combination. It is good in the sense of it gives you hybrid in CCA security guarantees. That's the core thing you want from a hybrid. The issue, though, is that it doesn't give you hybrid obfuscation. Because you have the two ciphertexts concatenated next to each other, the moment one of them becomes distinguishable from random, you will know this was a ciphertext and not a random string. So in follow-up work, we set out to answer the question, okay, how can we get hybrid obfuscation guarantees? And the proposal we make is called OINK. I'm missing a pig here on the slide. This wasn't there. It's not a technical issue, but I just realized now it should be there. Michael, maybe you should draw one later for the obfuscation talk. So OINK is short for the outer encrypts inner nested combiner, which sounds complicated, but actually is just a little tweak on top of a classical parallel combiner. You still encapsulate against both KEMs, and then you define one of the KEMs to be the outer KEM, and from that shared secret, you derive an extra key to encrypt the inner KEM ciphertext. So the result here is you still have NCCA guarantee following same arguments as for prior combiners, but then you get hybrid obfuscation, in a sense I'll explain in a second, with very low overhead, because it's just one key derivation, like a PRG call if you want, and essentially the encryption can be an XOR. So it's like super cheap to add this on top. And you might now wonder, well, but here you said you encrypt the inner ciphertext and the outer one is still there in the clear. So how does this give you hybrid guarantees? Well, this comes from the observation that, for example, for Diffie-Hellman, the Elligator encoding gives you statistical obfuscation. Even if discrete logs become easy to compute, an Elligator encoded Diffie-Hellman element will still be hard to tell apart from a random string. So actually we can use that as an outer KEM. This will kind of, like the obfuscation here will never break. And use it to encipher an inner one, which is only computationally secure, like ML-Kemeleon, which relies on the LWE assumption. The moment LWE breaks down, you can tell Kemeleon encoded public keys and ciphertexts apart from random strings. So in this way we can combine an outer and an inner KEM and get hybrid guarantees as long as one of them is obfuscated. The overall, the combined ciphertext will still look like random strings. And this is useful. Matilda already kind of pointed to that. I won't go into more details on these examples, but we use OINK to build two things. First of all, a hybrid obfuscated key exchange. So think of that as the hybrid replacement for the current OBS4 protocol, which runs in Tor bridges to connect out of sensor networks. This is kind of the hybrid version of OBS4. And you can use it, combining it with Cake, as Matilda mentioned just at the intro, to build a hybrid PEG with some novel properties, in particular giving you adaptive security against adaptive corruptions. Okay, so this is kind of the obfuscation part of the talk. And I want to switch to the second half. And for that, I want to take a step back, try to take a deep breath, and acknowledge that cryptography is brittle. It's maybe a debatable statement in the room, but maybe not. What do I mean when I say cryptography is brittle? What I mean is, if you implement a cryptographic scheme, there are at least two main goals you want to achieve. Your scheme should work in the settings that you usually want it to work, like be functional. And it should be secure against some kind of adversaries. How often our cryptographic schemes are, more often than not, can be implemented in a way that you get functionality, but not security. As in, you will have a scheme that runs and functions in all the normal operations, but actually the way it's implemented, it's completely insecure. To give you an example for that, like the most prominent one maybe, is from the setting of TLS and Internet Security Protocols. So think of a client talking to a server. Your task is to implement the client-side library, checking the server certificate. So checking whether the signature in the server certificate is valid. You're doing that, you might be writing code like that. And if that code looks mildly familiar to you, it will be because of these two go-to-fail lines here. So this is the code that was in Apple's SSL TLS libraries back in 2014. The code is famous for the go-to-fail bug, because this double go-to-fail line here meant that it kind of skipped most of the verification routine and essentially accepted any certificate as valid just because of like a minor typo in the program. This was interestingly not noticed for, I think, 1.5 years. Only then kind of people noticed that there was this bug. Why was this not noticed? Because everything was functioning perfectly. All the connection that you wanted to do would run through because all certificates were accepted. At the same time, you're completely open to man-in-the-middle attacks. Okay, so you might wonder, where is this going here? Like, we're in a KEM talk. Like, what does this have to do with KEMs? Okay, so for KEMs, remember that the post-quantum KEMs that we have today essentially all rely on the Fujisaki Okamoto transform, the FO transform. And without going into too much detail, the core part of the FO transform is that in decapsulation, what you do is, so the FO transform, first of all, just to recap, is taking a weakly secure public key encryption scheme and turns it into a strong in-CCA secure KEM. And so the way the KEM decapsulation works is you first decrypt with the underlying PKE scheme, but then a crucial task is that you have to re-encrypt the resulting key and check whether you get the same ciphertext out. That's called the re-encryption check in the FO transform. And this is crucial because, well, what happens if you might accidentally, or possibly because of like maybe an over-optimizing implementation, you skip this re-encryption check? Well, in all honest situations, you will not notice this, because all the honest encryptions will just go through, but you completely voided the in-CCA guarantee of your FO transform, and you're opening yourself up to even key recovery attacks in that setting. The question is, there's a question mark with that bug, so the question is, could that happen? Well, for that, let's jointly examine this way too small code, which is the libOQS implementation of HQC, the second NIST standard for KEMs. And it's the open quantum safe implementation, but it's essentially equivalent to the reference implementation from 6 months ago. And so this is decapsulation. You can't read this, but essentially what's happening here is some boilerplate stuff. There's decryption, there's re-encryption, and there's the checking that the ciphertext match. So this looks all good, except for a tiny bug hiding up here, which was introduced in some revision introducing implicit rejection, where the public key was incorrectly parsed. So this means that decryption happens regularly, but re-encryption happens with the wrong public key. Okay, you should immediately notice this because you will not get the same ciphertext that way. Unfortunately, there is a second bug hiding down here. Very unfortunately, a logical bug in the constant time equality checking for the ciphertext that flips the resulting bit, essentially. So all re-encryptions were wrong, but they were also all accepted. Now again, this was not noticed for 19 months. So in this project now, we ask ourselves the question, is there something, I mean, of course there's something you can do on the verification level, on the testing level, and you should be doing that. But we also have to be honest and accept that SSL libraries, HQC implementations will happen in all kinds of places, and we'll see different code quality. So our question as cryptographer, we asked ourselves was, is there something we can do on the cryptographic level to make cryptography a little less brittle in that regard? So can we tie security of a scheme to the basic functionality of the scheme? As in, do we make it such that if you screw up security in a kind of obvious way, you also break basic functionality along the way and will immediately notice this? And so the proposal, this is our proposal for what we call verifiable decapsulation. So to recap now in larger font. So FO kind of decapsulation, you have a decryption step, you have an encryption step, and you have the checking step for whether you get the same ciphertext out, and then you compute your resulting key. And so the idea is now, what if the encryption step doesn't just output the ciphertext alone, but some kind of confirmation that you actually did at least some core steps of this encryption step. We can never hope to protect against any kind of malicious implementation of that, but we want to catch accidental implementation errors. So the idea that we borrow from some prior work is to introduce confirmation codes, as in encryption step will also output some small code which says, well, you did the right thing along the way, and we can now include that in the key derivation, as in, if you happen to entirely skip the encryption step, or if you miscomputed with the wrong public key, for example, it should be highly unlikely that you accidentally get the same code. And so it will be highly unlikely that you get the same key. And that's precisely the tying of security to basic functionality. As in, the idea is, if you have a faulty implementation of re-encryption, this should lead to a noticeable KEM correctness failure. You will notice that because we'll not get the right key out. Okay, so maybe that's an idea which makes sense. The question is, what should that confirmation code be, and where would we get it from a post-quantum kernel? So for that, let's look at ML-KEM, and the question of how can we get confirmation codes out of ML-KEM. Again, in too small font for you to read, but still, this is ML-KEM's public key encryption algorithm. And there's one insight we can have here, which is that, as mentioned for the first half, ML-KEM ciphertexts are compressed before being output. This is mostly an efficiency gain for other reasons, but there's some compression going on, which means at the very last step of encryption, there is some entropy lost in the encryption operation. So the core insight now is to take that lost entropy and turn it into a confirmation code. So we can just use some uncompressed coefficients of the original ciphertext as our confirmation code. And indeed, for ML-KEM, it suffices to just use 2 coefficients out of each of the vectors to get a decent probability, in the sense of using only 12 to 20 bytes, depending on the parameter set, we can detect an incorrect, a faulty implementation of the re-encryption step in ML-KEM through a single test case. So just like running a single check whether encapsulation, decapsulation gives you the same key, with probability 1/3. So this will be immediately noticed in implementation, because that basic correctness check you will kind of always implement. And the overhead is pretty small for ML-KEM. It's at most 3.5%, 3.4% across all the parameters to get it. So that's the idea for ML-KEM. Let me spend a minute just on the rough formalism behind it. I'm happy to talk about that offline. So what we do in the paper is we give a confirmation code augmented FO transform. So first of all, we define what it means, what a good confirmation code is. And basically, good confirmation code is one that you cannot compute given all the inputs of encryption, which sounds a bit odd, because if you have all the inputs to encryption, you can of course recompute. But essentially, we're limiting the attacker in this confirmation code unpredictability game to not execute all the detailed, like all the inside steps of re-encryption. I'm happy to discuss that offline, but the intuition is essentially that an implementation which accidentally screws up the re-encryption step will not also accidentally implement all the re-encryption part correctly. That's kind of the logic behind. And then we follow the modular HHK transform and give a confirmation code augmented T and U transform, which include the confirmation codes and bind them into the key derivation, kind of like following, picking up the proofs and guarantees that we have to show that the confirmation code augmented KEM gives you the same security guarantees as you would have for the regular ones. And then finally, we can show that if your underlying PKE scheme satisfies this notion of unpredictable confirmation codes, then the KEM resulting from that augmented FO transform will have a noticeable correctness error if you make a mistake in the re-encryption step. That's like roughly the theory behind that in a very short glimpse, but just to give you the idea of like what the formalism is. Right, so to summarize, talked about obfuscation, hybrid obfuscation, and I told you about Kemeleon, which you can use to obfuscate ML-KEM public keys and ciphertext into random looking strings. The public keys even get a little smaller, if that's something you need for your application. We formalize this as an obfuscated KEM, and also show how to design a KEM combiner that has hybrid obfuscation guarantees. And on the verifiable decapsulation side, this is the idea of tying security to basic functionality through confirmation codes. We do this with an augmented FO transform. I showed you how to do it for ML-KEM with 12 to 20 bytes, giving you a reasonable detection probability. We also give the example of how to do this for HQC. And there a single byte is sufficient, and we implemented that in an extension or a version of libOQC. And that single byte included as a confirmation code would have immediately caught the bug that I showed you earlier in the basic test cases that were already shipped with the library. So it kind of immediately catches that. We're currently in discussion with NIST whether it's something to be considered for the final standard of HQC. Right. All the papers are online on ePrint, and That's all from my side. Thank you.
Thank you very much, Felix. We have time for one quick question. Yes, Fernando.
Hi, Felix. Thank you for the talk. I was wondering, when you describe the ML-KEM obfuscation technique, you mentioned you were using rejection sampling, using one of the layers. Doesn't that kind of change the distribution of? So I'm like, if I think of a kind of ciphertext, it's like a B sample.
Yeah.
Really a multi-letter B sample. By rejecting all the samples that encode to a higher order bit that is 1, are you not making the distribution farther away from random? Are you not like breaking the decision? Like, you're implying a distribution that doesn't satisfy the decision that you anymore, right?
Right, you're basically, yeah, you're right, you're rejecting some part of the key space and some part of the ciphertext space. So somewhat your LWE problem gets slightly easier. That's kind of my very rough intuition here now. For the randomness part, like you actually do get, well, truly random strings assuming LWE of the underlying thing. And it's just because you rejection sampling down to like a smaller set. But you're right, like the problem gets slightly easier as in you throw away some stuff. Similarly, that happens actually for Decapsulation and Elligator, that you throw away like half the points, roughly speaking. So basically, you lose like a bit of security in the Decapsulation group.
And would you then do like an extra gain hop when proving that you obfuscated KEM?
So in the security bounds for the obfuscated KEM, this bound shows up. This shows up as a small loss.
Let's thank Felix again.